So it started off with Dave Rice, who had years in the curtain wall engineering industry, and he opened up a business basically out of his attic. And he was just a one-person shop with basically two clients doing curtain wall calculations. So that's where we started off, and he incorporated it in, I believe, 1999, and kind of moved on from just curtain wall to doing hand railings, calculations, sunshades, panel systems, obviously the curtain wall as well, still window wall. Basically anything that's cladding, we have a hand in providing engineering calculations for it. So it grew from that one-person shop to today we have roughly 60 employees and 45 engineers on staff. When we typically are involved in the project, it's usually after the architectural drawings have been submitted and projects are going out for bid. So I have a few clients where we'll perform preliminary engineering for them so they can provide more accurate bids for the project. And usually that's like with a clip type system, like a clip and rail rain screen system, where we can provide a good rough idea for 90% of the building what your clip spacing is going to need to be. So that is a few of the clients, but mostly it comes from after the project has been awarded by a client, and then they come to us to perform the engineering calculations on their product they're providing.
Okay.
And typically who comes to us is, most of the time it's either an installer or a manufacturer. Those are your two largest. We're rarely ever hired by architects directly. The thing with the testing standards there is a testing standard or an ASTM for anything you want to put out there. So typically we aren't really referencing, us personally aren't referencing the standards. Usually they'll be included in the project specifications, say this curtain wall system needs to meet the E330 or water infiltration testing. So usually that's provided by the project specifications, it's directed by the architect or whatever the manufacturer wants to provide for a specification for their product. So it's hard to pinpoint which one you would really need to use. I mean, ASTM 330, which is a standard test method for structural performance of exterior windows, doors, skylights, and curtain wall systems. And we don't really have a good one for like stone panels or fiber cement panels for testing standards. So we typically follow those same testing standards. It is the standard test method for structural performance of exterior windows, doors, skylights, and curtain walls by uniform static air pressure differences.
Okay.
So basically it's just the air and water tests for those types of systems. And that's usually what you'll use for when you perform a wind tunnel, or not wind tunnel study, but actually doing a performance testing on the components. Okay, so finite element analysis, or FEA models, are basically you're breaking down the component into hundreds or thousands of small, I guess, pieces, if you will. So you're breaking down that whole element, and it's going to be into thousands of different little, tries to make it cube or trapezoidal shapes. And what it's doing is the stresses are sharing and how they're interacting from each individual node and shape throughout the entire component. So it's a much more accurate analysis of how stress is transferring through a component. So when we would use that is more so when it's difficult to determine based off of simple static calculations that are provided to us by the steel code, aluminum codes, or anything of that matter. So when we typically have to run an FEA model is when we have perforated panels that are unique shapes. They have unique patterns. Like I've had a panel that is in the shape of a leaf. They did a perforation pattern in the shape of a leaf. Well, it's really difficult to just kind of determine how that load is going to transfer through there. So we run models that will show us our stresses and deflections and shears through the components.
Okay.
So it's really when we get into complex geometry that we use that FEA modeling.
And then the systems analysis would be something like when we bring you our cladding substructure to hang like a Trespa or Fundermax panel then.
Exactly. We have basic, we have basic calculations that are provided to us by codes and then just by pure static calculations. And some of these stresses then are backed up by testing that they were able to provide a theoretical calculation for. So like a weak axis bending of a bracket, which is what we typically deal with Monarch, is with just do the L rail for instance. We have calculations. I'll check the whole section for bending, torsion, shear, tension, and then we also can do the local flanges for their bending through just the individual components of the L profile. And that's where we can use that analysis. However, like a job that someone else at Monarch had sent over about perforating that L profile, that is where we might be now going into FEA modeling to more accurately determine the structural adequacy of the system.
Oh, yeah, that's a great example. They're trying to achieve some type of open rate, and so you need to now analyze because the property has changed the L rail.
Exactly, and it's difficult to determine. So we have dead load hanging out there, and we have to make sure it can hold that weight. But now, instead of having a solid material, you now have 20% of that material taken out of the L profile. So it's not going to be a direct transfer from the front of the L profile to where it's attached to the bracket. So now we have to kind of go through a modeling software so it's not as conservative a check, because if I was going to check it with typical methods, so typical statical methods, I would have to reduce the section properties of the material by a considerable amount to be conservative, to make sure that we're not overstressed at those areas. It's not the best of answers, but it really depends on what kind of system we're using to hold up these rain screen panels and what type of system the rain screen panels are. If we're talking ACM panels, aluminum composite panels, or aluminum plate panels that have perimeter extrusions and clips, typically those are designed from the panel manufacturer that the clips and the perimeter extrusions will not fail before fastener pull-up. So typically when we're seeing that, we're just making sure that it's really about the load transfer. That's the main thing, to figure out what our fastener capacity is going to be, how the load transfers through the system. So the components that we have to go through to determine our load transfer are, of course, all of those that you mentioned. The negative pressure. Positive pressure typically isn't the issue, because most of the time that's just going to be bearing the substructure is going to be bearing directly into the structure, so it's not so much tension unless you have a high weight hanging off the building. But then you have panel weight, how far that panel weight is set off from the attachment of the fastener. So if we're 3 inches out from the building or 12 inches out from the building, that is a much greater difference on the tension on those fasteners attaching the substructure to the structure. And then fastener pull-out capacity is obviously the largest function of how or what we're looking at for the actual fastener performance.
So the fastener is what we, if we're a building person, we want to make sure the fastener is not going to fail.
Yeah, essentially, as a building person, yes, but when you're providing the brackets or the profiles, you'll want to make sure that the fastener is the weakest part of the system, right? So it's just a balancing act that way. And it depends on, how the load is transferred back. So you have a bracket with a back flange of, say, 4 inches wide that's attached back to the structure. And the fastener is installed right in the center of that 4 inches. Well, depending on how the load transfers, that could be more tension on that fastener than, say, if it's 1 inches over from the web of that bracket. So that's just extra eccentricities that we need to determine when looking at the fastener capacities as well. It's not like you're putting up your vertical L profiles in your brackets. That's going to be straight tension based on the wind load and the area. That is not necessarily what's going to be the tension on the fastener. There may be added tension on the fastener because the load isn't lined up directly over the fastener. Again, depends on the system. What's the defining factor is what type of failure mode will the system have. So if we have a brittle failure or a sudden failure, like you would have with fiber cementitious panels or especially stone panels like limestone or a quarried product. Well, a quarried product is going to differ greatly from one quarry to the next on what mechanical properties that stone will have. So there's where we use like a factor of safety of 8 on the bending strength of that material, just because it's so varied. Products that are manufactured, like a terracotta panel, or even the fiber cementitious panels actually manufactured in the shop, we can reduce that safety factor and per code, for all the codes, to maybe anywhere from like 3 to 5, just depending on what kind of panel system it is. But that's because it's a manufactured product. It's more predictable what those values will be for the modulus of rupture, bending strength, shear strength, and tensile strength of the material. And then again, pull out values for the fasteners. So in aluminum, that's not going to be a sudden failure. You'll see if aluminum profile were to start failing, it would start yielding first. So since we have more of a flexible material that has a yielding failure but wouldn't meet its rupture quite yet, we only have a safety factor of 1.65 as dedicated by the aluminum design manual, because again, it's a more predictable material. There's so much testing that goes involved with all these, and we have a good idea of how this profile will perform. Safety factors we do everything in allowable stress design. What a safety factor is, it's taking, so this panel will break or will exceed its bending stress at 3,000 PSI. All right, we apply a safety factor, so you divide that ultimate 3,000 PSI divided by, so we have a safety factor of 4, divide that by 4, or let's do 3, make it a little easier. Then we'll only be holding our stress value that we can bring it to 1,000 PSI.
Gotcha.
So essentially all we're doing is making it so it's technically 3 times, I don't want to say over designed, but you would be less likely for you to see a failure because we're not taking it to its ultimate failure value. Metal studs, typically we're assuming that we can only have attachment either from 16 to 24 inch horizontally on center. That's typically what we'll see for a range. And we like to assume 16 gauge studs because that gives us a better pullout value. We get a pullout value for a 1/4 inch fastener of around 260 to 280 pounds. When you go down to an 18 gauge stud, that same fastener only has a pullout value of around 130 to 160, let's say, pounds per fastener. So that's quite a big dip in capacity. So when you're selling to 18 gauge studs, you'll have less capacity and then therefore closer spacings vertically because we can't change the spacing horizontally, right? So you'll have different spacings vertically because you have so much less capacity in your anchor. Just because it's a thinner material, essentially. Even though the engineering firm that's providing the studs, they will meet the wind loads and everything else. But are they really accounting for clip systems being put every 44 inches vertically along the stud? Most likely not. And then when it comes to hollow block CMU, that's usually the worst condition we have. You can only account for maybe 1 1/4 inch minimum embedment at most with fasteners. So the most of them are designed for only 1 inch minimum embedment. So we're only looking for hollow block CMU of pull-out strengths of between 100 pounds and 150, because CMU anchors have to have a safety factor of 5. It's such a variable building material you're anchoring into. So therefore, again, if you're installing into 16 gauge studs versus hollow block CMU, well, that hollow block CMU will have much closer spacings of a bracket system. And then grout-filled block, you can get a lot better capacities because we can put embedment depths much deeper. So it just depends on what anchor, and each anchor will have different values that we're using, CMU anchors. For grout-filled CMU, they will have a lot of ICC report testing and ESR reports. Hollow block, there's only a couple I can think of that have the ICC reporting. And then into concrete, so there's, this kind of came when I first started here at Rice maybe 5 years ago, where we were finding in the codes that we are to assume cracked concrete. So that means, and I'm not saying that you see a visible crack in there, you'll see an inch wide crack. I'm talking about micro cracks that you can't really see with the human eye inside the concrete. This is occurring when the concrete is in tension zone. So if you have a wall and it's loaded from the back side, well, it's going to want to flex, and the inside will be in compression, the outside would be in tension. Concrete's pouring tension, so it has a tendency to do these micro fractures unless the concrete's designed with the proper reinforcement to prevent this. So the code tells us we have to assume cracked concrete when we're designing concrete anchors. And that those are much more expensive anchors. They're much beefier anchors, but they have this. They allow for the seismic zones too. Any anchor into like a seismic category C or D is going to have to require you to be cracked concrete approved, just because you're going to see seismic activity in that lifetime of that structure. So that was the biggest change that contractors saw when we're calling out. Used to be able to call out these small 1/4 inch diameter fasteners that only need to go in 2 inches deep. Well, now you have 1/4 inch maybe, but those are also going in 3 or 4 inches deep, or even much larger anchors.
Gotcha.
So the only way we can get around that from our aspect of design, where we're in the design, is going back to the architect or engineer of record and seeing if they will allow us to use non-cracked concrete anchors. Typically, that's difficult to get past because it's hard to prove that concrete will not experience cracking in its lifetime. So like with Monarch's brackets, you have a double bracket that's, say, roughly a little over 6 inches long. And then the wind load bracket, which is only roughly 3.5 inches long.
Yeah.
3.25 inches long.
6.5 and 3.25. Yeah.
Okay, perfect. And so when we're laying out these types of clip systems, the whole idea of these rain screen systems, if it's a vertically running system especially, is that it accounts for thermal movement. You will have clips along a vertical wall, and say we're running a rain screen system, which is say fiber cement panels, for instance, and we're attaching to these vertical L profiles. Well, that vertical L profile for aluminum, anything over 10 to 12 feet is starting to get to quite a bit of thermal movement. So that's why we like to limit our vertical spans to 10 to 12 feet. Also, we don't like to span over building deflection joints because the system can accommodate somewhere up to 3/4 of an inch movement vertically each direction. It's not going to allow for a total of 1.5 inches of movement. It allows more for just the thermal, which can be just roughly like a 1/4 inch expansion, 1/4 inch contraction. So when we're designing those types of systems, the reason why we have the dead load bracket, which is the double bracket, is it's 6.5 inches long, is because that will be handling the whole weight that is imposed upon that vertical profile. So it'll be holding the whole weight of that component. Well, since we have the 6 inches there, we can through fasten that profile to that clip instead of installing it into slots, because we want that to just be held in place. That is the point where we're not going to be able to allow any thermal movement. All thermal movement will have to be driven from that dead load bracket, either upwards or downwards. We like to stick with one bracket per profile that's a double bracket or dead load bracket, because we want to make sure it accounts for that thermal movement over that 10 feet. If every single one of them were to be dead load brackets, then there would be no allotment for thermal movement, and you could have issues because the profile is going to move. Thermal is a very powerful force. It's going to have to move somewhere. So it'll either try to bow out or bow in. We just want to prevent that by allowing you to have movement from that dead load bracket. So the reason why it needs to be deeper is because we need more fasteners to hold up the weight of the structure, since it's all that panel is being held on, say, 1L profile or 2L profiles. The wing load clips are smaller and have slots. Those only need to take wind load in and out, so they're taking less load of the system. So they typically can be smaller lengths because they don't need to take as much flexure. They don't be taking as much flexural or moment force through them. So we're installing those fasteners from the L profile to into the slots, again, to allow for that thermal movement. There is no reason why we need to dead load the entire L profile.
Gotcha.
And it's more of a waste of material if we're calling out double brackets for the entire length of profile, when more than likely we're not going to need it for the wind forces. So strapping, so we're talking about, say, 2 to 4 inch tall light gauge strap going from stud to stud to bridge the area in case you need to throw brackets in between stud spacings. So the issue with strapping is those thin gauge flat plates are horrible for deflection and horrible for stresses. Typically, the only ways to get those to work, if you're installing after the sheathing has been installed, so we're installing it right over the sheathing, is you would have to look at it as a tension member. So when we're pulling out, say, in the center of that span on that strap, or pulling out on that, it's going to restrict that deflection. It's going to have to send really high shears into the adjacent fasteners, into the studs. So you may need 3 or 4 fasteners at each stud location to account for those shears. And it's not really, who's really going to be putting in 4 fasteners per stud per strap? It's not very realistic, and it may overload the stud that we're not designing. I mean, studs are usually by others when we're doing this, so someone would have to check that down the line. The best way when we're allowing for strapping is if you can get it installed directly to the studs, in between the studs and the sheathing, because then we have that sheathing to help with the deflection issues when we're pulling out, because you have so much rigidity in that sheathing to help with the deflection of that strap. So if we're designing 18 gauge straps that are spanning 16 inches, we hardly could ever get that to pass through our calculations, because it's usually going to fail in stress and bending and deflection. When it's behind the sheathing, then all we really have to worry about is getting the stress to work, which is a little bit easier than the deflection, because there's just no depth. There's no depth to that, to a strap. So that's why it's so poor for deflection. If we have to call out straps over sheathing, it's not going to be like it's a 16 gauge material. It could be up to an 1/8 inch thick steel, 3/16 inch thick steel. It's just not, it just doesn't make sense. It's just too thick, too beefy of a route to go with that. It just doesn't seem like it's going to be cost effective to go with that strap.
Okay. It's good to know.
Yeah, I mean, again, there's ways we can get them to work, but again, they would have to take really high shears, and I don't know if it's realistic to expect them to be installed where they're going to have that many fasteners per stud strap. Also, the other thing thinking about those straps is, okay, we're spanning over the sheathing and waterproofing. If we're installing fasteners between studs, well, your fasteners will now be penetrating the vapor barrier and the sheathing between studs. So therefore, you'd have to worry about more waterproofing, because when that strapping deflects and comes out, it's going to pull away from the sheathing. So it's very difficult to then waterproof behind those fastener penetrations. That's why it's a little bit easier, again, when we have the strapping between the stud and sheathing, because it's not going, it would deflect the same amount with the sheathing, or it'd be so rigid it wouldn't deflect. So what we typically see, and I'm coming from a panel standpoint and rain screen system standpoint, there's plenty of others with curtain wall and sunshades, but typically it is, when we're seeing the architectural drawings, they're not fine details, so we have to not necessarily change things to make them work, but add more framing or subframing or stiffeners to make items work. So like coping panels around a knee wall or at the top of a building parapet. Those will be spanning 10 feet long, and they will not allow for, they'll be held from uplift at the ends, but on the front fascia, there's nothing preventing uplift. So you have to rely on these clips that are 10 feet apart from each other to prevent uplift, what can be upwards to 70 PSF. So we have to either change how we're attaching those coping panels to allow prevention of uplift along the fascia, or provide Z and keepers, just hold them in place. So that's from like a panel standpoint, that's the largest one I see, and deflection joints. Installation of panel systems spanning from floor to floor over floor deflection joints. Those floors have to allow for some kind of movement. So typically as an engineer, what we like to see is the subframing systems or the panels do not span over floors, so you don't have to worry about bridging that deflection joints. Because once you bridge that floor deflection joint, if that floor were to move down, well, you're gonna shear through your fasteners more than likely, that's holding that together, or something else is gonna be an issue, y'all buckling of your vertical frame members or whatnot. A lot of issues can derive from that, and it's not sometimes it's caught, sometimes it's not, or more of it's the engineer's challenge of that delegated design to figure out with a solution. So and typically we just like to say, again, start and stop at floor lines. You wouldn't have as much of an issue, or there'd be no issue.
Yeah.
That is the largest thing we see. And then after that, it's just more typical detailings. Maybe they're not preventing disengagement and just how they're drawn. So like, again, it's like with the coping panels, or we have a fascia panel that returns to soffit. Well, is there anything really preventing the negative disengagement of the system from negative loading? That's the common things that we see that we're not caught in architecturals.
Okay.
But for rain screen systems, in particular a system that Monarch would provide with those brackets and vertical profiles, its deflection joints is a major issue of concern, to always be looking how to accommodate floor movement. There's so many details that they have to get on paper. I mean, and they don't know, and the systems aren't necessarily specified out while they're making architectural drawings. So the system that you're bringing in may change from what they originally thought was going to be installed. So therefore, it's how are you supposed to know what the details are if you don't even know what the system is? So me personally, I'm the manager of one of the panel engineering groups. Typically what I focus on is composite panels. Like when I say that, I mean like ACM metal panels, flexible panels there. And then their panel systems for attachment to a substructure like Z framing, hat framing, Monarch's system with the brackets and vertical profiles, those types of framings. And then along with that comes fibrous cementitious panels. I do the perforated panel modeling. And then any other stone or rigid panel, phenolic panel, which is basically pressed paper or wood fibers essentially. So I really focus on those rigid panels. And then their framing system to the structure. Everything I do, I start at the exterior of the building and make my way to either the stud framing, the concrete structure, or the CMU wall. I really don't have any design of those areas. So that's not my area of expertise. I really stop from the exterior of the wall, really, with a structure. And then as an engineer, what I'm focused on is making sure that the components that I'm designing meet code. That's really what everything is just make sure they meet code. So performing calculations, designing determining the wind loads, the weight of the panel, snow loads, all the loads that are derived from codes. ASC 7 is typically where we derive most of our codes from. Determining how that transfers through the system and making sure every component in that system meets codes per stress, shears, fastener pullouts. Just making sure every part of that system is going to be meeting code and will be safe per code standards. Okay, so the structural priorities for when designing rain screen systems or whatnot. So first off, it's making sure that the wind loads are calculated properly. So we have wind loads. Weight of the system doesn't typically control unless it's like a curtain wall system, but for rain screen systems, unless it's a heavy heavy panel system, like a 2-inch thick limestone, those little light metal panels aren't really going to control for weight. You're still accounting for that, but those usually won't be the design concerns. Seismic conditions, seismic categories C or D, which you'll usually see those more towards the coast, of course, especially in the California, Oregon, and Washington areas. Making sure that you can accommodate the lateral movement as well as the vertical movement for those systems from seismic, allowing for vertical movement for thermal and for the floor movement joints, making sure the system is allowed to move. It doesn't tie everything together where you're going to have issues like we had discussed earlier. So making sure that, again, meets code, and that would mean deflections of members, deflections of panels. That'll be specified in the project specifications, but also per IBC, International Building Codes, they also direct us on what deflection limits typically should be, depending on what kind of panel system we have, whether it be rigid or flexible. And that's majority of what we're looking for when we're accounting for this. So when you're looking at, say, bidding a job or don't have an engineering background, what items you should be looking for more so, what your substrate is. Again, if we have hollow block CMU or stud or light gauge, 18 gauge studs, well, you got to keep in the back of your mind, you're going to have a lot closer clip spacing than if you're installing the concrete or thicker, like a 12 gauge or 16 gauge stud, assuming that the system fails due to the fastener. But then again, it's just checking through, making sure every component meets its individual code, like all the steel components meet the cold form steel manual or the structural steel manual, AISC in particular. The aluminum components meet ADM standards, aluminum design manual standards for stresses and deflections. I guess that's another thing for architects, going back to the architects, is making sure there's allotment for those seismic conditions. That's another one we see is we are having all this lateral force and movement. I mean, that we're going to have issues with joints. I mean, if our panels are only allowed to rack, say, 1/2 inch, but the joint's only 1/4 inch on the architecturals, well, that joint's going to need to increase. Otherwise, you're going to have panel systems hitting one another and possibly crushing or cracking. So that's another one from a previous question about not necessarily what architects get wrong, but some items that we see and need to identify and correct. So 2 reasons. Sometimes project specifications do require stamping of shop drawings. They require stamping and seal the shop drawings, stamping and seal the calculations. So it can be included in the project specifications why you'll need engineering calculations or support or guidance. Other than that too is you can make sure that the product that you're providing is safe and installed per code. So it's as safe as code provides. So if you were to have a wind event that's higher than what was provided by code, but it was designed per code, well, at least you're covering yourself because you did the due diligence of providing engineering calculations that confirm that this system should be able to handle typical code conditions. So it's helping protect yourself as well when it comes to if there's a failure, if you don't have engineering versus where you have engineering. Failures shouldn't occur nearly as much, if at all, when you have engineering, unless again you have an event that's outside of what code calls for, because we can't design for every single wind event, right? I mean, that wouldn't, you'd be over designing everything, and everyone already thinks we do that. So Rice Engineering has stamps in all 50 states. I believe all of Canada. There might be one province I'm missing out. Mexico, I believe possibly Puerto Rico and the Virgin Islands.
Oh, nice.
So, yeah, basically anywhere in the States we can do, and then most of Canada. So again, it's just to ensure building codes are met, ensure your project that all building codes are met. We can also, I know working with Monarch, is try to help optimize systems. So we can look at systems, you'll send over an L profile or whatnot. Well, can I just make this portion slightly thicker and cut down material on this portion of the component, and then maybe we can optimize how the system performs without increasing material everywhere and therefore cost. So we can help with optimization of any component or rain screen system. And not just optimizations of the systems themselves, but when we get a project, we can look at how it's being installed. And maybe there's a different way where they're not accounting for lateral movement, or maybe there's just so many parts and pieces we don't really need to meet codes or whatnot. We have to come into that again. So maybe we could remove some framing or space clip systems or horizontal railings out further, try to save money that way. Okay, so we can actually look at your details or see, okay, this is just not going to work here. You're not preventing, this panel can basically not even stay on the building from how this is installed currently. So we can help direct on ways to actually secure the system. Yeah, and then also items that are not constructible. So there might be times where there's really no way you can install this fastener, how it's drawn. Okay, well now we got to think of how we can actually install this system, because I mean, what's the point of providing engineering on something that you can't actually install? So then actually identifying what's constructible and what's not is also a service that engineering will be providing in their engineering calculation package. So I'm going to take it back to a previous answer and kind of tie it in, like with the cracked concrete anchors.
Okay.
20 years ago, I've been in this business for 20 years. This is what I'll hear. I've been in this business for 20 years. We never had to do this before. What's changed? Well, codes don't always, but tend to get more stringent. So something that worked 10 years ago doesn't work now. And that's usually due to, okay, we have more empirical data from, say, we have more wind speed data, or more, okay, this hurricanes are becoming more prevalent in this area. Do the wind speeds need to be upped? And that's always defined by the boards on whoever provides the codes, like the ACI concrete or the ASCE. It seems like every time we have an update to that code, we have different wind speeds that we're designing towards. So that is the biggest thing you'll see as a surprise. We're not trying to make anything more costly, it's just that to meet code, they're always finding new information to make buildings ultimately safer. And then there's also those clients that are working between states. How varied those codes could be from, say, Minnesota compared to Florida especially. So if they do all their work in Minnesota and they're going to start to do installation jobs in Florida, okay, that wind speed is totally different when it comes to that. ASC 710 for a typical building we're designing for 115 mile per hour winds in Minnesota, or if we were in Miami County, we're looking at 170 plus mile an hour winds. So it's knowing, and kind of, especially if you can get it with us early on, we can inform you before you underbid a project, hopefully, and you actually account for, okay, you're going to have to change a lot of spacings or system thicknesses, like gauge thicknesses on framing and all that. So I'd say that is a major surprise too, is just how surprised people are between codes between states.
Got it.
And then also reviewing boards too. There's some stringent reviewing boards that will review calcs and shop drawings.
Okay.
Typically you'll see that with like hospital or something, especially out in California where they have a lot of seismic, and that's where you'll see a lot more reviewing bodies. Even certain towns or counties, like I mentioned, Miami County and Broward County in Florida have much higher wind speeds than just Tampa Bay on the other side of the state. So local codes, local county or city codes can also be different. I know LA, for one, requires a COLA report, which is basically an ESR report. It basically is just a verified testing of each fastener that you can use in the job. So you have to have true test reports and that are stamped and certified by the reviewing board to use in that county. We will direct you to which fasteners to use that can meet those conditions. So I'll go with rain screen panel systems first. It used to be everything was just a sealed joint. So when we were installing these metal panels, you have like this 5/8 inch joint in between for like an ACM or just typical metal plate panel. And so you'd only have one layer protection of water infiltration. Well, now we have all these rain screen ACM systems that have like a little ACM insert, and they will allow, it'll stop basically 90% of the water, but say 7% of that moisture gets in. But we're allowing for that moisture to get in. There's like 2 layered systems for water infiltration. Those are also tougher to design. So it's getting those, but you're more worried about water infiltration, and you don't want just a one step to prevent anything, right? We want some redundancy in design so that we can prevent any water infiltration issues or actual failures. Another one that we've seen coming across here a lot more is a push to going green. So what I mean by that is more thermal performances. More companies are wanting to see thermal modeling of systems. And again, a lot of times I'm seeing a lot of these rain screen systems that are clip and rail, because that's less penetration through the insulation layer. Because your bracket systems can be every 44 inches, where before we're fastening through every 16 or something like that. So it's just to prevent, going green is a major item that we see coming through. And it's just driving how we're doing all these systems.
Okay.
Another one is we're seeing a lot of European designs and components coming through. And what I mean by that is a lot of glass fiber reinforced concrete panels, phenolic panels, and stone panels. Those are becoming more and more prevalent. Those companies that are overseas are starting to get into the US markets again, and architects are really pushing to have those types of components on their cladding. So we're seeing a lot more of that, which will require some kind of subframing system. And again, that ties into another is quick installations. And quick installation would be a componentized subframing system. So you have these brackets that you can install on the wall, then you throw up the rail. It has adjustability. You don't have to shim out. So before it used to be everything was Z's and hats.
Mm-hmm.
So you'd have a solid Z going across this building, and you'd have to shim out maybe every other fastener, depending on how off plumb the wall is. Well, now with systems like what Monarch has, where you can have adjustability in the field, that's becoming a big market whenever we're talking with contractors.
Yeah.
Because they want that adjustability. You have to have that adjustability. And this was talking too with a few other engineers that have been around here for 25, 30 years, that have even more experience. But again, pre-engineered systems. So you can just go out and pick this system, and we already know that it has testing to back it up. And engineering calcs ran on it for, like example, if a lot more E330 testing on systems. So you can just buy the system and already engineered. You're not going to need to worry about it. You can spec it out as an architect, throw up on the wall. We're good. Just make sure that the wind loads are still within that realm, which speeds up the whole engineering calculation process and is easier for architects and contractors to determine what system to use. I've seen something like a lightweight stone panel where they do a panel veneer, which is maybe a 1/4 inch thick, and it's like granite or limestone or whatever kind of stone we want to use here. And they do a honeycomb backer, like this aluminum honeycomb backer, and that'll be like 3/4 of an inch. So if the architect wants an inch deep panel, well, now instead of an inch thick of heavy stone, you're now a 1/4 of the weight of that. I can see that becoming a major push in the future. Hopefully, it's a lot nicer to engineer when it comes to those actual bracket systems. Obviously, everything's going to get more expensive, right? Materials are more expensive and that, so we have to find ways to optimize and maximize the materials and the spacings of systems. So that's a never-ending push, but I might as well mention it nonetheless. I already mentioned subframing system adjustability. Again, that's going to keep carrying out.
Yeah.
Lead requirements. So basically that energy efficiency again, they may be wanting more recycled content in panel systems. So for instance, like those glass fiber reinforced panels, if they need more recycled aggregates to use in those panels, for instance, I could see that being more of an issue or concern going forward. Again, that also helps with trying to cut prices on everything that's increasing. Possibly along with that lead requirements, more fiberglass, maybe involved like fiberglass thermal clips or something of that nature. Just because then you don't have as much thermal bridging between your subframing system and going back into your structure. The only thermal transfer, or the most thermal transfer then, would only be through the fastener penetration. That would bridge. You can see that becoming a larger portion of the market. Another big one too is when I first started, project schedules from start to install, okay, I mean, you may have a year and a half of planning and actual manufacturing. I'm only seeing the project schedules getting more and more and more condensed. Now it's everything is, okay, we can get that done in 8 months, 6 months. Engineering needs to be done in 2 or 3 weeks, something like that.
Okay.
So condensed project schedules, which again is really going to push that subframing system adjustability and the pre-engineered systems.
It's interesting you mentioned honeycomb. I don't know if I've told you, Rhett, but we brought to market at the end of last year a new honeycomb deform nut rail.
Oh yeah?
Yeah, so if you do have any of those honeycomb jobs come along, we now have something. It's on our website and everything. And we did a really fabulous couple jobs in Los Angeles already, or Santa Clara. And so it's another exciting product that Monarch's brought to market.
Perfect, yeah. It's just being able to cut that weight down by a fraction is just,
yeah.
Especially when you're trying to provide also your own adjustable subframing system, that only helps even further, so we don't need to rely on having 2 or 3 dead load clips per profile.
Exactly.
It's out even more. Another item too would be that we could see going forward is NFPA 220 more enforced. So that's the fire rating of panel systems. I don't know if you recall, but in the news a couple of years ago, there was a building in, I want to say London.
Yeah, it was London.
Yes, where we had the ACM panel fire. And there's going to be more fire rated composite panels for sure. But also, it seems like there'll probably be more testing on a lot of components when it comes to this.
Mm-hmm.
You can only see more components being tested for this. And there needs to be, we'll see in the cladding especially, is, okay, was there a horizontal break at every floor, or was there fire allowed to just chimney effect, which is what it seems like. It just made a chimney effect where there was no horizontal break between the vertical panels, so that fire could just spread all through the exterior of the building straight through the panels, and then it creates a chimney effect. Well, is there going to be more requirements where we have to have a break, so we have to have some kind of insert at every floor line so this doesn't occur? So we stop a fire at that floor, prevent the quick spread of that.